Hello, I'm Dr. Jeff Cloxton, and this is my colleague, Sarah Skosen. We're from the Nanotechnology Characterization Lab at the National Cancer Institute at Frederick in Frederick, Maryland.
In the next few minutes, we will show you how to prepare samples and determine the hydrodynamic diameter of a nanoparticle using batch mode dynamic light scattering in dilute aqueous suspension.
This protocol is a simple, accurate, and non-destructive method to determine the size of nanoparticles. We will give you guidelines for making successful size measurements in the nanosize range. At the end, we will conclude with a discussion of relevant standards and data analysis. Be sure to wear personal protective equipment, lab coat, gloves, and goggles.
Sample prep will be done in a hood to minimize dust contamination.
Dust particles, on average, are greater than 1 micron or 1,000 nanometers in size. The intensity of light scattered is proportional to the diameter raised to the 6th power. Thus, larger particles will scatter more light and will interfere with your results.
Before we begin, you will need the following items: a cuvette and lens paper for wiping the outside of your cuvette. You will need your dispersant media, which needs to be filtered through a 0.1 micron filter or smaller, your sample, clean tubes for filtering your sample into, a loading syringe, and a 0.2 micron syringe filter. You will need the appropriate sized pipettes and tips, a vortexer for mixing your sample, and for cleaning the inside of your cuvette, you will need isopropanol, distilled water, and nitrogen gas. For this demonstration, we will be measuring 30 nanometer colloidal gold, which is a NIST reference material. To start, I will be diluting my sample 1:1 in my dispersant media. Our dispersant media for this demonstration will be water.
Typical sample concentration is 1 mg per mil. This may be adjusted depending on your sample's scattering properties.
Make sure that your sample is mixed well. I will then add my sample to the dispersant media to make my dilution. Mixing your sample again after you make your dilution. Next, I will be filtering my sample through a 0.2 micron filter. Before loading your sample, you will want to pre-rinse your filter using your dispersant media. After loading the dispersing media, I will add the filter to the syringe.
Choose a filter size such that the sample is not removed from the solution or modified during filtration. For example, we are measuring 30 nanometers colloidal gold. Hence, we could use either a 0.2 or a 0.1 micron filter. A 0.02 micron filter would filter out the majority of the sample.
I will then remove the filter from the syringe in order to load my sample. After placing the filter back on the syringe, you will need to discard the first 4 drops of your sample. The rest of the sample can be placed into a clean tube. Now I am ready to clean my cuvette. I will do this by rinsing it several times with distilled water.
The cuvette we are using has quartz windows. Alternatively, a cuvette with optical quality glass windows can be used. Cuvettes can accommodate different sample volumes ranging from 10 microliters to 1 milliliter. Choose the appropriate cuvette capacity depending on available sample volume and instrument requirements.
I will then rinse once using isopropyl alcohol and dry using nitrogen gas. Next, you will want to rinse your cuvette using your dispersing media. I will do this by pipetting the dispersing media up and down several times in the cuvette, and then discarding it into waste, making sure to get all of the liquid out of the bottom of the cuvette. We are now ready to load our sample. Before loading your sample, you will want to make sure that it is mixed well. Since we are using a micro cuvette, I will be loading 100 microliters of our sample into the cuvette.
Do not overfill the cuvette, as this can lead to thermal gradients, which will impact measurement accuracy.
After placing the cap on the cuvette, you will want to inspect to see if there are any air bubbles. If you have air bubbles, they can be dislodged by tapping gently on a soft surface, checking again to make sure they are gone. Lastly, you will want to wipe the outside of the cuvette with lens paper to remove all dust. Checking to make sure it is clean. You are then ready to make your measurements. Place your cuvette into your instrument in the correct orientation for the instrument you are using. We will be using a thermocap to keep constant temperature.
The layout and software will be different depending on the instrument. However, the key parameters that need to be inputted will be the same. The first is dispersant. This refers to dispersing medium. In our case, water was used, so select water from the drop-down list. Next is temperature. This refers to the measurement temperature. In our case, we'll be using 25 degrees Celsius. A minimum of 4 minutes equilibration time is recommended. Longer equilibration times will be needed for larger sample volumes. Next is cell. This refers to the cuvette. Select from the drop-down list the appropriate cuvette. Finally, measurement. 3 measurements are required. However, we recommend a minimum of 10 measurements to ensure sample reproducibility and accuracy. Once all the key parameters have been inputted, begin the measurement by pressing the Start button. Once the experiment is finished, we can now perform data analysis. The screen shows 3 panels: the count rate, the correlogram, and the intensity distribution plot. The count rate is a measure of the intensity of the scattered light. Refer to your instrument's manual for an acceptable count rate. The scattering intensity depends on the particle's size, refractive index, and sample concentration. Since the sample concentration can only be modified, it can be adjusted accordingly to give acceptable count rates. The correlogram is a plot of the correlation function versus the delay time. Its shape should be smooth. For example, it should decay exponentially to a flat baseline, and the y-intercept, or amplitude, should be stable. Noisy correlograms and/or fluctuating amplitudes can be due to dust contamination, concentration variations due to aggregation or precipitation, or dirty cuvettes. The correlogram is used along with an appropriate algorithm to generate the intensity distribution plot shown here. Please refer to your instrument's manual for details on the algorithm used. The intensity distribution plot has been expanded for clarity. From this plot, we see the measured size of our sample is 27.7 nanometers. Using cumulance analysis, we can report the z-average, or the intensity-weighted average over all sample populations, and the polydispersity index, or PDI, which is a measure of the broadness of the distribution. For our sample, the z-average was 27.7 nanometers with a polydispersity index of 0.179. This low PDI value implies a monodispersed sample, and typically, PDI values less than 0.2 are considered monodispersed. Finally, DLS is a first principles measurement technique, thus calibration is not needed. However, reference materials are available to verify correct instrument operation and sample handling. NIST reference materials are available for this purpose.
We hope that we have helped you understand how to successfully perform this protocol.
For more information on this method, please refer to the full protocol at the address shown on your screen. Your feedback is appreciated.
Thanks for watching.